We'll just wait one more minute and get started then. Okay. Okay, hi everyone. Welcome back to the Ultra Quantum Matter Summer Seminar Series. So we'll get started right away. So our first speaker is Dominic Williamson from Stanford University, and he's going to tell us about stability of topological order in tensor network states. So Dominic, go ahead.
Great, thanks. Yeah, so I wanted to talk about something today that is sort of, if many of you may know me for work on fractons, is actually mostly not about fractons. So it's still about topological order in 3D though. And the question is about whether when you have tensor network descriptions of states of topological order in 3D, you can have stability to perturbations to the tensors, which is a property you would want if you ever want to use these things for numerics. And I'll tell you in a second that basically it's already known in 2D this doesn't work, but it turns out in 3D that in some settings you can have stability, and that's sort of the upshot. And this is ongoing work, so hopefully on archive soon with Clement Delcamp at MPQ. And it's also basically following on some line of research that was suggested by Norbert Schuck and Frank Verstrada actually quite a while ago when I was still in my PhD. So yeah, here on the title slide, you can see a nice tensor network that actually ends up being stable and a stable Clement. And I'll also tell you about some other tensor networks that are not stable. So here's an unstable Clement. So just as like a little reminder of what's going on with each of the different tensor networks I show you, I'll keep the stable or unstable Clement there. Cool. So as an overview, the problem I want to think about is when you have this tensor network, which basically you can think of as some sort of function that takes in some local tensor that's like a small piece of data. And I'm just drawing it with some notation I'll explain in a minute here. You can then produce a state out of this, a ground state of a many-body system. And we're wondering about what happens if we perturb this tensor. And it turns out that, okay, we know that if this state we produced has topological order and is gapped, perturbations to the Hamiltonian it'll be robust against those, like the phase will exist in some finite region due to some result by Michalakis, Bravi, and Hastings. But in some previous work from actually going back 10 years now, it was already looked at what happens if we think about perturbations to the tensor rather than to the Hamiltonian. And so if these all map to perturbations, the Hamiltonian would be done. But it turns out they don't. That was basically the point of the first paper at the bottom there. These can actually map to some perturbation that's sort of non-local on the actual spin level, because we're kind of doing something inside the tensor network that's not really a physical operation. And what this can do, which is explained in these two nice papers here, is basically that some of these perturbations can just pop anionic excitations into existence locally. And basically when you have like a finite perturbation strength in 2D, you have like a finite density of these things, which gives you a phase transition instantly. Okay, so these ones get an unstable Clement in 2D. And the thing I'm going to tell you about is what happens if we look at various different tensor networks in 3D and analyze what happens to their stability. Cool. So first I should introduce some of this notation I was already using in the previous slide. Tensor networks are some nice class of ansatz for ultra quantum matter because they can kind of avoid things like the sign problem, and they give you some control over scaling sort of the amount of entanglement in your states. So you can almost think of them as some generalization of like mean field theory, where that's like a zero entanglement, and then you have some parameter which you can just increase, which is usually called a bond dimension, to increase the amount of entanglement. And you can look at the scaling of that to sort of try and capture the true physics of what's going on in the problem. The simplest and very successful class of these tensor networks that's non-trivial is the matrix product states, or MPS in this slide, which are basically given by taking as an ansatz for a 1D spin chain that the coefficients of the wave function are given by products of matrices. And the matrices are organized with the locality of the 1D spin chain. And I've got this little picture here, so let me explain this notation a bit. Each of these boxes is some tensor A, which has 3 legs, and on these legs you have some dimension. For the physical dimension, it will match the dimension of the actual physical spin you have, and that's the one that points down. And then on these sideways pointing legs, those are sort of internal degrees of freedom. The dimension of them is something you control in the ansatz. And so whenever you specify some basis configuration, you get a number out of this thing. And I will use some convention that if we ever have like a pair of legs being connected and not sticking out, then you sum over them, basically. Okay, so coming back to this, now you can see the bottom diagram matches this trace of matrices summed over all of these open values. So the I values would live on these open legs. And I'm being a little bit sloppy here. Sometimes this confuses people. I'm sort of identifying the state with its coefficients, but of course we chose a basis for that. And so this picture here is basically the coefficient once you fix a basis on every spin. But when we're doing like many body sort of stuff, we don't care about what the local basis is on each spin. So I'll be sloppy and just refer to this as the state, but really it's up to some just individual change of basis on every spin. But again, that doesn't matter for us. Okay, so now getting towards what I want to talk about. Although tensor networks have proven very useful in 1D, there's quite a lot of active research going on about using them in 2D, sort of numerically. I think already a lot of theoretical understanding is there, but there's some exciting progress on doing better and better numerics, and I'm sure one day this will be really standard. And in 2D, you need sort of a higher rank tensor that you can put onto some lattice, a 2D lattice, and then you can track this up to make some state, which is called, in this case, a projected entangled pair state. That doesn't really matter. I'll just call it a PEPS for the rest of the talk. And these things are capable of describing the ground states of strongly interacting 2D many-body systems. And if we start to think about like what sort of things we want to describe in 2D, what sort of physics would be interesting to us there, the most obvious thing that's not in 1D is sort of topological order, if we're just thinking about gap systems, say. And these tensor networks are capable of describing topological order. And instead of talking about some more maybe realistic topological order like spin liquids or fractional quantum Hall states, I'm going to think about the most simple toy model. Because I'm going to be thinking about some sort of some fundamental limitations on describing topological order in these tensor networks. Okay, so the simplest toy model for topological order, this is Z2 topological order, is Kitaev's toric code, which is just some commuting projector Hamiltonian where the spins dimension 2 and live on the edges of a square lattice in 2D. And we have these commuting terms, a Plaquette term given by some product of 4 x's and vertex terms given by products of 4 z's. Hopefully this is familiar to everyone. This x terms generate some kind of symmetries that commute with this Hamiltonian, if you like, which I'm going to call a one-form symmetry for the purposes of this talk. Basically, I just mean like codimension 1 deformable loops are symmetries. And if you kind of cut these string symmetries open, you get some excitations, which turn out to be sort of non-trivial superselection sectors. As in, you can't create one locally, you have to create them in pairs. So if I have an isolated one, there's no way to get rid of it, basically, with a local operator. Okay, and you have a dual version of this from the Z terms, another codimension 1 symmetry. And this creates another kind of anionic excitation, which I'll call M. And you can sort of put these two together to get another fusion of these two excitations, which I'll call psi. So the topological data describing this toric code, basically these 4 different superselection sectors, the vacuum, E, M, and psi. And it turns out that's everything. And they have this simple Z2 times Z2 fusion rule. And they're called anyons because although E and M are both sort of bosonic with themselves, and psi is fermionic with itself, if you braid E around M, like do a full braid, you get a -1 phase factor, which you would not get for bosons or fermions, which I've just indicated with this S at the bottom there. Okay, so basic review of toric code. Maybe the most important thing to keep in mind from that was that we have these non-trivial superselection sectors, which you can't create with local operators. Okay, so how would you come up with a tensor network for this ground state? It turns out to actually be quite easy. Because the Hamiltonian is this commuting projector Hamiltonian, you can just directly come up with a projection onto the ground space, which is given by basically projecting onto the lowest energy eigenvalue of each of these terms individually in the Hamiltonian. And technically it's frustration free as well, which means you can minimize all of them. So this projector doesn't end up being zero. So one strategy for getting a ground state instead of just a projector into the ground space is just taking some simple state, say like the product state of all zeros on the edges, and then hitting it with this projector. And as long as this doesn't give you zero, which in this case it doesn't, you get an unnormalized ground state. And it turns out in this case, if you pick the all zero state, because this is already in basically satisfying all of these vertex Z operators, they just are absorbed by the state. They do nothing on it. And we're just left with these X projectors, which are the Plaquette projectors hitting this all zero state. And so why does this give you a tensor network? Because basically each one of these projectors itself is a tensor, and the all zero state is some very simple sort of zero bond dimension tensor network. So you can kind of put these things together to get a tensor network description of the ground state with a low bond dimension. Let me just explain the notation I'm using to describe this projector in a few slides. So I need two kind of basic tensors, actually three in the rest of this talk. One is this delta tensor, which just gives you one if all the legs have the same value. And I think for the rest of the talk, I'm always going to be doing qubits on the legs. So each leg has two labels like 0 and 1, or plus and minus, depending on what you prefer. And this simple black dot tensor is just a delta. It just says all these legs have to be the same, and I get a 1, otherwise I get 0. It has this sort of blob property that if you put two together, you get a larger delta tensor. And it also has this kind of pruning property. If you stick in a plus state on one of the legs, you get rid of it basically, and just get the delta tensor on less legs. It also has these symmetries. And basically you can flip all of the legs at once, and it'll be the same tensor, or you can apply a Z operator to any pair of legs. Okay. Now there's the other dual tensor I want, which is this plus tensor, is just given by basically applying a Fourier transform or Hadamard matrix to all the legs of the delta tensor. So it's basically just the delta tensor and the other basis. I think I should mention here, I'm going to be sloppy about normalization for the rest of the talk. Like, I'm never going to bother including any factors of 1/2 in the talk, just for simplicity. Okay, they're all there in the paper, so everything works out fine. Yeah, so this Fourier transform up to normalization basically just gives you -1 to I times j as mod 2 numbers. And it has this commutation property down here shown with X, which it basically flips X operators to Z operators because it changes the basis when you pass through it. Okay, so this thing is basically the same tensor in a dual basis. It has the same properties, except now this sort of pruning state is a 0 state. And it has dual symmetry, so all Z's on the legs are a symmetry and pairs of X's are symmetries. Okay, I think that's all you need to know about those tensors. And if, okay, maybe I should come back to this slide. Why was this the same as the projector up to normalization? Basically, because if you fix the incoming leg to be 1 on one of these plus tensors, it's just doing an X matrix. It's applying an X matrix to that leg. If you fix the incoming leg to be 0, it's doing the identity. And this black tensor is just summing over all 0 and all 1. So basically you get all 0, you do all identities on the 4 sides. You get all 1, you do all X's. So it's just basically doing a sum of all identity plus all X, which is the same as this P projector on a single plaquette. Okay, so if you take your toric code and you imagine putting like the 0 state onto all edges, you hit it with this big projector, and then let me just not draw that original lattice so you can see the diagram better. The tensor network you're left with is this one. It's just some network of these plus and delta tensors. And we can start to understand its properties. So I think the most important thing about these tensor networks of topological order is that they have some kind of internal or gauge-like symmetry. I say gauge because it's like a symmetry, an internal symmetry of the wave function that really does nothing physically. It's just like a different way of writing down the same state. And in this example, you can understand these as coming from symmetries of these individual building blocks. So you have this little loop of x's you can apply on the internal legs. And when I put an x there, technically I mean when you contract up this whole tensor network, you put an x operator on that leg when you contract it. Okay. And the important thing about this is that this loop is sort of deformable. You can move it anywhere in the lattice, which is kind of reflecting this one form symmetry. Like a general version of this was studied in this reference at the bottom for any kind of G symmetry, any finite group. And then like a super general version, which also covers string nets, is in the bottom reference. But for today, I'm just going to focus on the sort of simplest case. Cool. So yeah, like I said before, this sort of internal symmetry is reflecting this one form symmetry. And I think for the other examples I'm going to show, this is like a common thing. There'll be some X stabilizer group, which is like giving you a symmetry, and that's going to map to this symmetry inside the tensor network. Now, if you cut this open, you make some excitations. And what does this look like internally? It's going to be just a line of these X operators ending somewhere. So that's what one of these E excitations look like in the tensor network. And you can see that it doesn't depend where this line goes because you can move it around freely through the tensor network. So you only know the location of the endpoint excitations as you should. If you apply instead like a string of Z, a Z string operator to make a pair of excitations of type M, then if you just use the properties of the tensors, these end up just becoming 2-point operators internally in the tensor network at the two endpoints. So basically, in this case, you can see that the string operator position doesn't matter because basically it's not even recorded in the tensor network, only the endpoints are. And you can sort of understand these internal excitations as being like domain walls and charges kind of under this internal symmetry. So if you sweep this internal symmetry over these charges, you'll get a -1, which is reflecting the braiding statistics between E and M. And yeah, there's some more general version of how excitations work in these two references at the bottom. But for today, this simple network will do us the trick. Great. So we want to think about what happens when we add perturbations to this tensor network. So we basically have this state on like 6. You can think of this tensor as like a state on 6 qubits. So we could think of some generating basis of Pauli's and applying it. I think because of the periodicity in the tensor network, I could pretty much shift something acting on the left leg to something acting on the right internal leg. So I'm just going to consider these two legs, the rightmost and upmost in this case. And I'm also not going to worry about perturbations on the physical level because we basically know that we're going to be protected to them. So let me first think about these X perturbations. Because of the properties of the tensor, I can just move these to physical perturbations. So I'm not going to worry about these because essentially they map to like physical perturbations, and we know that this ground state and its parent Hamiltonian will be robust to these if we pick sort of the Hamiltonian I showed as the parent Hamiltonian. So this is where the problem comes in. We can also consider these Z perturbations, and this time I've written it to the left for convenience. It doesn't actually matter which leg I wrote it on, the left or the bottom, because of the symmetries of the tensor. But because this perturbed tensor basically has a different charge under this internal symmetry, it ends up being an anionic excitation. And so this single perturbation to the tensor can like pop a single anion into existence, basically in the tensor network. This is a bad thing. And like I showed in sort of the overview, it's previously been worked out that essentially adding these perturbations that are charged under the internal symmetry induces some sort of anion condensation sort of instantaneously. So, it seems these things should be unstable, basically. And we can be a little bit more careful about this in this, or a bit more precise about this in this case, and actually do a mapping to a stat-mech model, and we'll see that it has like an instantaneous phase transition. I'm going through this much detail for the simple example of this 2D toric code, not because it's new, but because basically the way we do this example carries over directly to all other of these stabilizer models, which can describe sort of more interesting topological order. And we can use that to see the stability sort of instantly of those models by repeating this process, but for them. So let me continue to describe in great detail this 2D toric code. If you take the overlap of this tensor network with itself, you kind of get a contraction of the network with itself along the edges, and it collapses to the thing I'm showing on the screen here. basically just the same one as before, but with none of these sticking out indices. This is because we're evaluating this overlap to a number, so there shouldn't be any sticking out indices. And the way to see why you get this is because on the edges, you'll have two of these plus tensors hitting, and you can just sort of blob them into one and split them. And then on each plaquette, you'll have two copies of this delta tensor, one from each layer, but they have this property when they're sort of contracted with one of these edge tensors that they collapse. And so you end up with only one copy of each of those. I then want to do one extra change of basis. Maybe I picked a bad basis to start with, if you like, and flip the edge tensors to being these delta ones and the vertex tensors to being these plus ones, because I want to massage this into looking like a stepmic model that will have some relation to the phase transition I'm talking about. Okay, so in this step, I basically just use this duality with the Hadamard transformation of the plus and delta tensors to flip the middle one to a plus and all the edge ones to deltas. So now back to the overlap tensor network. It's this kind of stepmic partition function where I have my classical spins on the edges, and I'm going to label those by plus and minus 1 because it's more usual to do it that way. And then on every vertex now, I have this delta condition, which basically says that the strings coming in have to satisfy some mod 2 fusion. Okay, so if I write that as an equation, it's like a sum over all configurations and then a product over all these plaquettes of this delta condition. And I can just kind of massage that into being exactly a sort of lattice gauge theory in 2D in the limit of like infinite temperature, where I'm ignoring normalization again. Probably you want to take this limit in a way where you normalize it so everything's not blowing up to infinite, which is fine. So yeah, we've just sort of gone through some re-massaging of this kind of pretty trivial overlap of the state, the unperturbed state with itself, into like the zero temperature limit of this lattice gauge theory. But what happens if we now think about the perturbed tensor network? And let me write the perturbed tensor network state as just ket epsilon, where epsilon is tracking this perturbation that was the troublesome one. And I'm going to just do a trick and change the normalization of the whole state by this root epsilon factor, overall root epsilon factor for each tensor. And you'll see why in a second. And then we want to see what this overlap is mapping to now. And basically it's going to be the same as before, but now we have these perturbations that we're introducing some z's onto the plaquettes. The simplification comes where basically the edges just go the same as before, they collapse. But now when we have this sort of collapsing of the plaquettes, only the diagonal terms survive. So only when there's a z in both the plaquette on the bra and the ket do you get a non-zero contribution to the overlap. So that's just written as this equation. And then again, I'm going to do this dualization, but now the only thing you need to keep track of is if there's like a z on the plaquette, it's going to get flipped to an x. So instead of it being like a mod 2 sum of the edges coming in being 0, when there's an x there, it's mod 2 sum of the edges coming in being 1, or minus 1 if you want to do it in the spin basis, the classical spin basis I'm using. Okay, so if you look at the first term here, up to this absolute value of epsilon inverse, which is coming from a normalization, and the fact that one is a bra and one is a ket, so you'll be conjugating, so you get a real number. The first term is basically the same as the Hamiltonian before. You just have this delta condition in every plaquette that the product of these spins is 1. But when you have, you also have like the superposition of this plaquette with the plaquette where the x is applied now, coming from that z perturbation. And on those plaquettes, you have the product being minus 1 with this small parameter epsilon. And just for some more massaging to try and make this look like a partition function, I'm going to reparameterize this real number, positive real number, with an exponential of inverse temperature. Okay, and now if you just replace the previous equation like this, you'll see that basically I'm either going to get an e to the beta or an e to the minus beta factor on each plaquette. And you can just rewrite that in terms of the formula below. So essentially I'm just doing the sum over all configurations and a product over all plaquettes of this function, which is just a rewriting of the line above. And then you can realize like this thing is exactly just the stat-mech partition function of this lattice gauge theory at a finite temperature. And the temperature is set up such that when the perturbation epsilon goes to 0, the temperature goes to, the inverse temperature goes to infinite. So the real temperature is going to 0. Okay, so the upshot of that is that we have the mapping of this overlap to a classical stat-mech partition function. But you could ask, okay, just because we have this, are the phase transitions of these things really matching? So we know that the phase transition of this partition function in 2D classical lattice gauge theory is going to have a 0 temperature phase transition, which we think is going to tell us that the corresponding 0 perturbation strength phase transition will happen on the quantum model. But you can be sort of more sure about this because you can look at how the sort of symmetries are mapping too. So any product of an X operators on the quantum state, expectation value of that maps to some expectation value of a spin operator, a classical spin operator. And this is kind of a version of something that's been discovered with tensor networks a long time ago in this reference at the bottom. And so it turns out that actually part of these set of operators that map directly to the classical operators are some generalized order parameters for like a one-form symmetry breaking phase transition. So it also turns out the way we did this perturbation that we retain on the quantum state, we retain this symmetry, this one-form symmetry generated by the Z stabilizers along the whole path. And so the kind of, on the quantum side, the phase transition we're doing, you can think of as like this one-form symmetry, spontaneous symmetry breaking, which is measured by a loop order parameter of this X quantum operators. And this maps to this loop order parameter in the classical gauge theory, which will measure this confinement deconfinement phase transition. So because these order parameters match exactly, the phase transition locations should match. Yes. So that just basically confirms what we already suspected, that with this perturbation at sort of infinitesimal strength, we'll already have this phase transition. So verdict on that one is an unstable Clement. Great. So now let me get to the point of this. Yes.
Scroll back. So what exactly is the operator that perturbs the system to drive this phase transition?
I think it's not a physical operator. It's some perturbation to the tensor you're using in the tensor network. And it can be in a non-trivial superselection sector, the perturbation to the tensor, which means it won't be a local operator at least. I guess maybe you could think of a non-local operator that's doing it.
So in what sense is this a deformation of the original system?
So the deformations, you have the state, which is given as a function of this tensor, and I'm doing it in a translation invariant way. So there's one tensor that I then contract to give me the state. And then I can just make some perturbation to this tensor, which is a function of this, let's say beta. And then I have a class of deformed states as a function of beta.
But if you just start in the old-fashioned way with a Hilbert space in a Hamiltonian, what should you do in order to drive this system through this phase transition?
So I think you can get the same sort of phase transition, but obviously if you do any Hamiltonian perturbations, it won't happen instantaneously because you're in a topological phase. But basically if you added like X perturbations to the physical Hamiltonian and you made them very strong, you would be doing sort of the same condensation, because eventually when you make these X perturbations strong enough, you'll go through this sort of anion condensation phase transition.
So this is not an infinitesimal deformation of the Hamiltonian, it's a large deformation.
Yeah, I think exactly. I'm not sure exactly how to think of it as in terms of the Hamiltonian, because basically maybe one way to think of it is we're adding completely non-local operators to the Hamiltonian, which means when you add an infinitesimally small perturbation of totally non-local operators, we can just destroy everything. Does that make sense?
Well, you do something. I'm just trying to understand what it is you're doing. You're clearly doing something interesting, but I'm just trying to understand what it is.
It's, well, I guess it's a variational class of states, and the small variation of that, of the states, doesn't correspond to a small variation of a local Hamiltonian. You would need like non-local terms in the Hamiltonian for it to be a small variation. But maybe, yeah. You could.
So can I ask?
Sure.
In terms of local observables, is this a continuous deformation of the state?
Um, I think it would be, but I'm not totally sure off the top of my head.
Thanks.
Okay. Yeah, let me move on. So this is sort of just redoing this 2D toric code example, but we're interested in, and it ends up being not stable. And there's sort of, in these previous references I showed you, there's some arguments that basically no tensor network in 2D should be stable to these tensor perturbations, essentially because when you do this small variation to the tensor, it can be basically adding completely non-local terms to the Hamiltonian, which the topological phase shouldn't be stable against. It's only stable against local small perturbations to the Hamiltonian. But now let me go to 3D while I still have a little bit of time. Maybe I can take another 5 minutes. In 3D, we have the toric code model again. This still on the edges of this time a cubic lattice. And we have these plaquette terms, which are basically the same with all orientations. And then we have this vertex term, which is like Z again on all vertices. I'm sorry, all edges adjacent to a single vertex. Great. And this time these two terms aren't quite equivalent. One generates like a two-form symmetry, or these deformable 1D loops, and one generates a one-form symmetry, or these deformable membranes. And if you cut these open again, on one hand you get some sort of point-like E excitations, and on the other hand you get some kind of flux loop excitation. And these loop excitations, you can't break them up, basically. They have to appear as closed loops, which will come as important in a minute. So let me just really blast through this one. Basically, if you pick one basis of the PEPs, it is unstable. So in this basis, you have this one-form symmetry on this internal sort of gauge-like symmetry of the tensor network. And the perturbations can be a charge under this symmetry, like a point-like charge. And then when you look at the perturbed tensor network, you again get like this condensate of these point-like charges at infinitesimal strength. So without being more careful about that, I'm just going to claim it's unstable for the same reason as 2D. But we now have this new feature, which is in the other basis, we have a kind of different, very different symmetry. So this is like a two-form internal symmetry. If you like, on every loop of the tensor network, basically, we can apply some loop of X operators, and that will give us a symmetry. And now the charges under this are different, quite different to the ones under this one-form internal symmetry. So if we think about the tensor network on like a cube, there's some constraint given by the fact that if we apply the symmetry to each plaquette, every single plaquette of the cube, all 6 of them, it just does nothing. It doesn't do nothing to the state, but it does nothing to the tensor network itself. It just leaves it invariant. This means that if you can't have like a single Z perturbation on one of these plaquettes, because basically you could take the single Z perturbation, you could apply this do nothing transformation, it would pick up a -1, and so you'd have like state equals minus itself, which doesn't make sense. So this basically gives you a constraint that you need to have like an even number of these Z perturbations to the plaquettes, which is just another way of rephrasing in terms of the tensor network that these M flux loop excitations have to come as loops. They can't come as like isolated point-like excitations, or you can't break a single piece out of a flux loop and have it living alone. So yeah, I'm nearly at the main point. Now, if we consider the sort of perturbations that are not immediately local on the Hamiltonian to this tensor network, we get a sort of different thing happening. Instead of some sum over these local non-trivial superselection sector particles popping up everywhere, we have a sum of all lengths and then a sum over all loops or products of loops of that length on top of the ground state. And so this already kind of naively seems like it's quite different, because essentially the things you're making, you can always sort of put them in some bowl and then it will be actually a local operator. It's not immediately obvious that this thing actually, it still doesn't map to a local perturbation on the Hamiltonian side. And the kind of way to see that is that the scaling of how a loop is going to enter the ground state, the perturbed ground state, is scaling with the length of the loop, not the sort of the area of a surface that loop encloses, which is what you would get if you perturb the Hamiltonian. So maybe it's kind of a borderline case, and we need to be a bit more careful to decide whether this is stable or not. But you can essentially just do this thing I showed you before, which works essentially for all of these sort of X and Z only CSS stabilizer Hamiltonians, where you map this to some classical model. And in this case, it's just like the 3D version of the one I showed earlier. You get these delta conditions on plaquettes. And let's substitute in the perturbation strength for some inverse temperature. Then what you get is just, again, a sum overall spin configurations on edges, and then a product of overall plaquettes of, I think that's right. A product of overall plaquettes of these, this perturbed kind of constraint, where the perturbation strengths essentially map to this inverse temperature. And that's exactly just a rewriting of the classical partition function of this Z2 lattice gauge theory, some inverse temperature. And this one does turn out to have a finite temperature phase transition. And again, you can be sort of a little more careful and make sure that these phase transitions actually match each other. But this goes through again. So basically the order parameter, the loop order parameter on the quantum state will map directly to this like loop order parameter on the classical model. And so in this case, you have this tensor network, and because of the kind of constraints on the perturbations, it does end up being stable to these like internal deformations that don't map to local physical perturbations. Great, so the verdict on this one is good, it's stable, Clement. And then I think because I'm at the end of my time, let me just quickly summarize. So for this 3D toric code, in one basis, we still had these point-like charges and this internal one-form symmetry that was similar to 2D, and that one ended up being unstable. But we could have this different kind of symmetry that couldn't happen in 2D, basically, in a non-trivial way, which is like this two-form internal symmetry. And the perturbations in that case were these flux loops that were kind of constrained to appear as loops, which ended up being enough to make it stable. And then I said I wasn't going to mention fractons, but I can't help but mention them a bit. We also in 3D have the possibility of all sorts of these crazy fracton models, even with these simple Hamiltonians. And we can apply the same logic to them. I didn't talk about them because the result ends up being kind of boring. That basically for any fracton model you look at, any sort of pure fracton model, all the charges are point-like and can be isolated. And so when you look at the tensor networks, they can have quite interesting symmetries. So for example, this X-cube model can have this sort of cage net or sort of planar one-form symmetries internally. But the perturbations are always these point-like particles. So they could be fractons or linons, depending on the basis you choose, but that is enough to make it unstable. And similarly for this kind of more crazy type 2 fracton model, you have a sort of fractal symmetry of the tensor network, but the perturbations end up being non-trivial superselection sectors that are fractons, and adding these perturbations still is enough to make the tensor network unstable. Okay, so that brings me to my conclusions. I think it's just reiterating what I've just been saying, so I don't need to actually go through it. And maybe I'll just mention sort of future directions. One thing would be really nice, which we can't currently do, is we think that these sort of logic we're applying should apply beyond the sort of simple class of networks we can do an exact mapping to some stat-mech model with, but we don't have ways to actually prove this. So we think that whenever basically the perturbations of the tensor give you some point-like thing, which depends on the tensor network symmetry, it should be unstable. And when you have these constraints that make loop excitations, it should be stable, but we're lacking the ability to actually prove that more generally. And then this possibility of stability to perturbations maybe is promising for like thinking about some kind of usefulness of these tensor networks in 3D. But I think the actual algorithms, no one is really thinking much about 3D at the moment, and maybe that is a interesting future direction to actually try and use these tensor networks to simulate some 3D many-body systems. So with that, I'll say thanks for your attention.
And thanks, Dominic. Maybe we can take one or two more questions, quick questions before Adrian's talk.
Question? So this instability in 2 dimensions, what does it mean for numerics? Does it mean that if you're just practically trying to look for a ground state, you will never get anything with topological order, or?
It depends on the way you're doing the numerics, I guess. But if you're setting it up with this sort of PEPS numerics where you have, you're really using this 2D tensor network, I think it means that if you're doing like infinite system size numerics, so you can do it numerics in different ways, and like broadly you can do it such that you actually have a finite system size, or you can do it when you directly kind of take continuum limit with like some translation invariance. thermodynamic limit. And then I think if you're in the finite system size case, you could still kind of see topological order up to some system size. I guess it's just saying that if you really take the limit, thermodynamic limit, it shouldn't be in the topological phase. But yeah, maybe the sort of size up to which the patches still look like they're topologically ordered will depend on this perturbation strength. So maybe, yeah.
Thanks.
I'm a little confused about your statement about the 3D toric code. So you said if you write it in one basis, it's stable in the sense, and if you write it in the other basis, it's not. But those are the same state, though, right? The unperturbed states are the same. Is that correct?
Yeah, this is funny because it's all something about just different ways of writing the same state. Exactly.
So, but that means that the perturbations to which it's unstable, you just can't write in a simple way in the other basis. Is that right? It's a higher bond dimension or something.
Yeah, I think if you wrote it in the sort of stable basis, then the unstable perturbations, all the sort of unstable perturbations are non-local on the physical level. But then if you write them on this sort of Hamiltonian level, the choice you make can make these non-local things local. But in the choice of the stable one, the sort of non-local things still map to non-local things. If that makes sense.
Yeah, I see. Thank you.
Can I ask a related question? The PEPs you constructed, is that just taking the Kramer's Wannian duality of contracted with a product state for?
Yeah, I think it is just that. It's the generalized Kramer's-Wannier duality applied to the trivial state.
Mm-hmm. And you have two of them because you can gauge the zero form or gauge the one form.
Exactly, yeah.
Uh-huh.